Okay, another new one here. Um, so new functional groups or types of compounds: alcohols, ethers, thiols. Of course, as we know, as we're you know coming to find out, lots of molecules contain multiple different kinds of functional groups, but we're focusing on three new ones now: alcohols, ethers, thiols. Okay, and we'll do them in that order. So alcohols are compounds that contain an OH functional group. Now, sometimes that is in the slide. It's noted here in the slide. That's also called a hydroxyl group. Or if OH, and this happens sometimes if we're naming an alcohol or a compound with an OH group in it, and that OH group isn't the highest priority functional group, that OH group might be referred to as a hydroxy substituent. Okay, but if it's a highest priority functional group, then the compound itself is named as an alcohol, and we'll learn how to do that as well. Here's just some examples of different types of compounds that we may or may not be familiar with. Ethanol, not methanol is a one carbon alcohol, and so we call it, here it is over here. It's the simplest alcohol there is. But if you add another carbon, so you end up with CH3CH2OH or C2H6O, we call that ethanol. And ethanol is in a number of different commercially produced products, including alcoholic beverages. It is the alcohol in what's referred to as, alcohol for consumption. It's also ethanol is also one of the main components, or I should say the main antimicrobial component in lots of different hand sanitizers. Now, some hand sanitizers are isopropyl alcohol-based hand sanitizers, but a large majority of them are ethanol-based hand sanitizers. And speaking of isopropyl alcohol, and it's kind of a fuzzy picture here, but rubbing alcohol has traditionally it's definitely got antiseptic, antimicrobial properties also. And that has traditionally been different concentrations, anywhere from 60 to 90% isopropyl alcohol is typically referred to just kind of generally as rubbing alcohol. Although now, I've noticed I'd seen rubbing alcohol at some point in a pharmacy or drugstore, and it was actually an ethanol solution. So, but going back forever, normally we think of rubbing alcohols as isopropyl alcohol, or again some concentrate, a mixture of isopropyl alcohol and water typically. So anyway, okay, let's actually, I bet we'll do almost for sure, nomenclature next. Now, so new functional group, right? At least one new rule. And we have a lot of the tools already to name these, but the new, I guess the change here is that alcohols, the suffix, I should say, that's used to describe alcohols, their name, the suffix is OL, just like you'd expect. If you think about alcohol, last two letters are OL. Same thing here. That OL designates a compound as an alcohol. Okay. And we do remove the E typically. Now, that's not true if there are two or more alcohol functional groups, and we name those as diols or triols. What I mean is we leave the E, but in this case we remove the E from the parent, from the alkane parent name, and just add OL. So let's actually practice this. It's easier to discuss this when we're talking about a specific example, that's for sure. So let's look at A here. And I may need to, I don't know, maybe we'll have room here. I think I have a slide here if we don't. Okay. I'm going to actually turn off the sound here. Okay. So let's take a look at at A here. Okay. Again, as always, we're going to find and number the parent. And I'm just going to go ahead and say there it is right there. And again, we could have done this, right? And that would be okay too. You'd come up with the same name, okay? Longest continuous chain is 6 here, okay? Now, the substituents are one we've seen a lot, a methyl group, and that OH group, which again, if it were named as a substituent, it would be a hydroxy group, but it's not a substituent. It's actually what's giving or what's designating this compound as an alcohol. So it's definitely numbered and designated that way, but the OL takes care of essentially the OH group, the OL suffix, I should say. So putting this all together, right, this methyl group is at the, and that would be my question for you, where is the methyl group and where is the OH group? What numbers are they at? Are they all, what are their number locators is what I'm getting at. Now, one of the things you have to, again, remember back to is if there are multiple functional groups and I'm trying to decide how to number this, I've got to prioritize them based on that functional group priority list, which, again, you will have that attached to your exam, so you'll always have access to that. You just need to know how to use it. It turns out if you look back at it, alcohols are higher on the list than alkanes or alkyl groups, so I'm going to number this such that the OH group gets the lowest priority rather than the methyl group in this case, which would be numbering from the left if that got had the highest priority, right? And we were giving it the lowest possible number. So in this case, right to left to give the OH group the lowest number. Okay, so methyl is at 5, so I can actually start to put this thing together. 5-methyl, 3-hexanol. Now, just like with some of these other ones, there's a couple of possibilities here. So I'll write the other one. The 3, kind of like with alkenes and alkynes, the 3 could come in front of the whole parent chain, essentially, or it can go right in front of the suffix. So this could also be 5-methyl. Ooh. 5-methyl. Hexan. 3-ol. So notice we did take that E off of hexane, right, and added OL. Okay. All right. Let's try, let's actually try C next, and then we'll grab B and put it onto a different slide. There's something that's a little bit, a little unique about B there. So good chance to pause and give C a try. Okay. Now I'm going to circle up the parent, and again there's multiple that would work here, but it's important to recognize that my parent has to, it can't be this one. Here, let me just show you something. Notice how our parent has 3 carbons. That would not be correct. We need it to, again, because it has that higher priority OH functional group, we need our parent to include the carbon that's attached to the OH group. Okay, so in this case, it's got to be this one. Okay, or I should say it could be this one, right? Because that would also work, or it could be this one. Right? Those all include the carbon that has the OH group attached. So I'll just go back to this one. Okay, and if I'm numbering, again, for the same reason we just discussed, and I won't rehash that, we number 1, 2, 3, and we've got 2 methyls, right, and an OH group that we need to designate or account for in our name. So this now becomes something we've done before, 2,2-dimethyl, right? There's that Greek prefix that indicates there are 2 of them, and we have to locate both of them, right? So 2,2-dimethyl, 1 propanol, 3 carbons, right? Or 2,2-dimethyl propan 1-ol. Okay, 2,2-dimethyl propan 1-ol. Yeah, either of those would work. And also, again, if you were to go online and look at synonyms, in some cases, if we're talking about the functional group that's the OH group in this case that's making this be classified as an alcohol, if it's at position number 1, sometimes the 1 is dropped, but I always want us to include it, again, just to be as explicit as we can, as clear as we can. So yeah. All right, so I'm going to redraw this compound. Make sure I got it right. I think that was it. Yeah, okay. So a couple things that are different about this one as compared to the others is, well, it's cyclical, right? So that's important. We need to designate that in the name, and we've done that before. But I want you to also recognize, now, if this compound had been, it wouldn't be surprising to see something like that, okay? And the reason I say that is, you know, sometimes we're not worried about the three-dimensional character of the molecule, that, you know, whether the substituents in this case are coming out at us or going back in. But there are some situations where it's very important, and we do designate it. So if I was talking about this one, I wouldn't worry about stereochemistry, right? I wouldn't worry about, remember, and I'm going to throw this out there, I'm kind of spoiling it for you, but I'm going to throw out cis and trans. I wouldn't worry about cis and trans. But in this case, I have, right, wherever I got this problem, or whoever made up this problem, you know, did use dashes and wedges. And so just as a reminder, sometimes it's helpful. I don't know that it's helpful necessarily from a nomenclature standpoint, but do you remember drawing Haworth projections for these cycloalkanes? And we you know, it's helpful, if for nothing else, to actually, let's number this, and I'll number the ring here as well, the Haworth projection ring. I'll call this one carbon number 1 and 2 and 3 and 4, 5 and 6. So now, having drawn that Haworth projection, kind of the skeleton form of it, what we see is, if we were to take this, and hopefully this will be helpful, I'll maybe tell you why I'm doing it in the first place here in a second. But if I take this and I actually, you know, think about, so these atoms, the way they're drawn, are all in the same plane. And so you basically are just twisting this up towards you, such that, again, we have a flat representation. Now, think about this, the carbons 1 and 2 with me for a second. Make sure I have, okay. So remember, if there's something on a wedge, there's also something on a dash. Same thing here. There's something on a dash, and that dash would actually have a, that wedge would actually have a hydrogen on it. And so if I kind of take this flat two-dimensional representation and I pull it towards myself such that carbons 1 and 2 are coming out at me, in that case, then my OH group would be pointed up and my hydrogen on carbon number 1 down, right? Again, that's what I'm seeing anyway. The way I'm looking at it here is hydrogen's backing away, OH is towards me, and so if I twist it around such that 1 and 2 are coming out at me, OH is up, hydrogen is down, and then hydrogen on 2 is up, and looks like a methyl group, right, is down. Okay, so again, the reason I did this, now there are hydrogens everywhere else, right? All of those other lines have hydrogens on either side. It's just that now, remember, if I have 2 or more substituents, those things, because the ring isn't opening and closing, you know, I guess without me breaking the ring, right? If I can't interconvert between the cis and trans isomers of a disubstituted cycloalkane, or disubstituted cyclohexane in this case. So if the plane of, you know, we're flattening out that molecule such that I have one thing pointed up, right? This is up, and one thing below, down, right? This is what we refer to as a trans relationship, which we've discussed before. Again, I don't beat this to death and spend 20 minutes on it. But if they were both up or they were both down, that would of course be cis, because they would be on the same side. Now they are trans because they are across from one another, on opposite sides. So all that to say, I have to write, as we've done before, trans out front. Then I can figure everything else out, right? So now let me go back and think, okay, what else do I need to worry about? Well, I have an OH at position 1. I have a methyl, here it is right here, right, at position number 2. Now I know it's just a dashed bond, but remember, that's the line that ends, so there's a CH3 group there. So I would call this 2-methyl 1-cyclo, remember cyclohexanol, or trans 2-methyl cyclohexane 1-ol. Okay? All right. So what's next? Okay, and I mentioned this just a second ago. It is more than possible. It's plenty of molecules have more than one OH group. So if a compound has 2, we call it a diol, sort of generally, or 3, a triol. Those happen to be the suffixes as well. And you see some examples here. Okay, I would use these. I'm not going to do them because they're already done for you. But I would try to, if you want some practice with these, try to reproduce this on a different piece of paper. Same thing here and same thing here. And you have their names right here. So you can produce them on your own and then come check yourself. Now, diols are often called glycols. So anyway, these are the ones in parentheses are actually, and this molecule is a really common compound as well. We'll see it a ton later in the course when we talk about triglycerides. But anyway, more to come on that. But the compound, or the names I should say in parentheses there, those are common names, and you don't necessarily have to know those. Okay, just the IUPAC names. So let's make a different one. Let's just like make one up here. Just so we get a little extra practice with this. And again, there's some other ones on the slide. So what if we had something like this? Well, let's do this. Let's do something like that. Okay. So a good chance for you to give it a try. And actually, let's put another. Let's put a CH3 right there. Okay. So give it a try if you like. I'm just going to go for it. So I'm looking for the longest continuous chain, right? So my parent, and it looks like it has 1, 2, 3, 4, 6. Yeah, it looks like it has 6 in it. Now, this is an interesting one because we're like, well, how should we number this? And it does actually matter in this case. I would argue, right, well, if you number from this side, right, the OH groups certainly have a higher priority than the methyl. If I number from this side, I have an OH group at 2, right? I want to give it the lowest number possible. From the left, an OH group also at position 2. But notice how I also have this methyl. If I number from the left, right, the other group also would have a lower number locator than if I numbered from the left. And so that kind of breaks the tie. And we've seen examples like that before. So let's number it this way. 1, 2, 3, 4, 5, and 6. Okay? So then this becomes, if we put it all together, remember it's going to be a diol. And if you go back and look, and it's in the slide somewhere, I won't flip back to it, but with diols and triols, we actually retain the E on the alkane parent name, so we keep it rather than getting rid of it and then just add, in this case, diol as the suffix, still with locators. So this becomes 3-methyl, looks like 2,5 hexane diol. Notice the E, I kept the E, right? Or 3-methyl hexane 2,5 diol. Okay? All right. So, okay. Physical properties again, right? Another new functional group. So we revisit physical properties here. So a lot of times, and we'll do this again, I'll just give you a couple of examples, similarly sized compounds, and we'll predict boiling points. But one of the statements here on the slide, I want to just add a little bit to it. It's not just, we should put higher melting points and boiling points. Some of these are liquid, is at room temperature. So boiling points. Whoa, sorry. I guess it says boiling points. For some reason I thought it said melting points. So higher boiling points and melting points. Let's also put and water solubilities. We'll see that intermolecular forces, dramatically influence, lots of physical properties, as we've seen before, and certainly this is, another example of that. This is no exception to that. Okay. So another thing again that I like to do is make these tables, and I'll give you an example. And again, these examples are only good examples if we're looking at compounds that have different functional groups but that are themselves similar in size. Remember, size is important when we're thinking about these physical properties and the intermolecular forces that govern them. So we just looked at that statement, right? Of course, these alcohols have higher boiling points, melting points, solubilities as compared to other similarly sized compounds, including alkanes. Okay, let's try to talk about why that might be true. Okay, so if we say, I guess we could write molar masses here, but often what we'll do, right, is polar or nonpolar. Okay, strongest IMF in a pure sample. Okay, and then we could do boiling point. Okay, and we'll just do degrees Celsius. So, you know, I guess I suppose we could even name them as well, right? What would this one be? Good practice, right? This is 2-methylpropane. And this is, right, we just got through naming these, right? So 2-propanol or propan 2-ol. Both are acceptable. Now, I need to add this up, I guess, real quick. 12, 20, 40. This is about 58 grams per mole. Again, back to that size thing. They need to have similar molar masses. And this one would be about 60. So they're really close. A couple of molar mass units are, again, those are close. Now, hopefully, again, back to this, it gives us some more good practice, right? Notice what kind of compound this is. This is a hydrocarbon made only of carbon and hydrogen. So if we're thinking back to designating it as polar or nonpolar, it could never be polar, right? No matter what, because it has all polar bonds. But if we're looking at this compound here, and we could even remind ourselves, right, that if we want to redraw this in a little different way, right, this is sometimes helpful as well. We remember, right, there are those vectors that describe this. Or another way of doing the same thing is partial negative, partial positive, right? And so we get a feel right away for the fact that this is polar for reasons we've discussed lots of times before. And again, I don't mean to trivialize this. If it's something that you need some additional practice with or some additional help with, please, let me know and we'll talk through it. But this is definitely polar. Okay. And you could probably guess, the rest. I mean, the relative order of boiling points, but I'll give you actual numbers for these. But okay, so strongest intermolecular force in a pure sample for totally nonpolar molecules. Remember, the only thing they can ever do or participate in is dispersion or London dispersion interactions. And for molecules with OH groups, now it's not just molecules with OH groups that can do H bonding. Excuse me, but there has to be, in order for things that have that don't have OH, NH, or FH, but they do have like an O, an N, or an F. Remember, there has to be something with an OH, NH, or FH around. But in this case, not to go on too many tangents, we've discussed this stuff before. So H bonding is the strongest. And again, there's a vast disparity in terms of the strength of those interactions, and it translates to a large difference too. So this is actually so 2-methylpropane is a gas at room temperature. It's like negative 12 Celsius degrees about, and isopropanol or 2-propanol. By the way, this is that isopropanol or isopropyl alcohol. It's that rubbing alcohol we were talking about, but that's just colloquial. It's not like an IUPAC name. Our name was correct when we came up with. This is about 82 degrees Celsius. So again, major difference there. Okay, next thing. We're back to reactions. So again, we look at these characteristic or common reactions for a particular functional group. So for alcohols, what's kind of nice about this set of reactions, now we need to lay a little bit of groundwork here, but what's kind of nice about dehydration reactions is they are the opposite, the reverse of a type of reaction we've already seen called a hydration or hydration of an alkene. And so if we can, we'll show this to ourselves. We'll try to make this really clear, but it's really helpful to recognize that fact. Now, the first thing that you see maybe that jumps out to you on the slide is this sort of symbolism here. Alcohol is being classified as 1', 2', or 3', or also we say primary versus secondary versus tertiary. So what I want to do here is just describe that maybe with a statement. So here's what we mean by that. So okay, I think we're okay here. Primary alcohol. Okay, so we'll just put the carbon attached to the OH group is also attached to one alkyl group. Okay, now you'll see right away where this is going. Secondary alcohol. I guess I'll just write them out. The carbon attached to the OH group is also attached to two other alkyl groups. Now, tertiary, we'll look at examples. Just want to actually make sure we understand this sort of from a definition standpoint. Okay, 3' tertiary alcohols, so the carbon attached to the OH group is also attached to 3 alkyl groups. Okay, so let's get a little bit of practice with this. So let's pretend I draw, and I'm just going to sort of do some random. Okay, let's try. Maybe that's okay. We can. Okay. Let's try these. Okay. And I'll just do maybe in a different color here. So again, I want us to focus on, in all of these cases, I'm going to circle because I think it's a good practice. I'm going to circle the carbon, and notice this is line angle, right? These are line angle formulas. So I'm going to circle the carbon that's attached to the OH group because that's the one I'm kind of focusing in on when I'm determining what we call the substitution of the alcohol, okay? Whether the alcohol is classified as primary, secondary, or tertiary, right? So if I'm doing that, in fact, let's just do it for all of them, right? Okay, because then if I go back to these definitions, I'm going to start on this top left one, right? The carbon that's attached to the OH group is also attached to how many other alkyl groups. Now, if you want to really, again, you definitely don't want to screw. If you're like I want to make sure I don't mess this up. So what you could do is also write the other things that are attached, even though it's bond line. You know, if you see it right away, don't take the time to do it. But you could also write in the additional the additional things attached to carbon, which in this case are all hydrogens, right? So in this case, right away, you're like, oh yeah, well, this over here is my alkyl group. And really all you have to identify is the fact that, it's attached to another carbon, right? Because an alkyl group is a carbon containing group, right? And so the fact that it's attached now to one carbon right here means, and then two other hydrogens, right, in addition to the OH group, means there's one alkyl group, right? So you're just looking for a point of attachment that's a carbon, that's an alkyl group. So technically, well, not technically, I mean, in any way, right, we're going to classify this as primary, this one, that first one there, okay? Now, I'm going to go through, how about this? I'm just going to go through and write them, and you can go through and prove them to yourself. Maybe I'll just describe them as I go, but this one ends up being secondary, okay? Two alkyl groups. There's also a hydrogen. You can prove that to yourself. You can write that in as well. Okay, this one over here, primary. Okay, there's another alkyl group, or I should say there's an alkyl group right over here. And let me just get this while I do this. So alkyl group, two other hydrogens. Okay, this one over here, you're tempted to think, man, maybe that's tertiary or maybe it's secondary, right? Because I have two alkyl groups here. But remember, if we're looking at the carbon attached to the OH group, it's really just attached to one other alkyl group. Okay, and maybe, I don't know, maybe it's worthwhile to just circle the alkyl groups in all these cases. There's the alkyl group. Here is an entire alkyl group, right? The first point of attachment, there's a carbon, still two hydrogens there. And in this case, there's actually three separate carbons or alkyl groups. So that one becomes tertiary. So if we finish this up, this actually is primary, and this one's tertiary. Okay. Make sure we did okay on that. Yeah, looks okay. Now, the reason we did this, again, we said we need to lay a little bit of groundwork here. Let me go back to here. Is a couple of reasons. It turns out that depending upon whether you're dehydrating primary, secondary, or tertiary alcohols, so dehydration means to remove water, as you might guess, dehydration, right? But in this case, you're removing actually an H from an H and an OH from adjacent carbons to form an alkene. That's really what's happening. So the water is formed by pulling an H off one carbon and an OH, the alcohol OH that is, off of another carbon, and in between those carbons you put a double bond, okay? And again, we're going to look at several practice problems. The other reason is, in some cases, it's possible to do that a couple of different ways. And so, it is important for us to revisit substitution. And we can also predict it a different way based on, and there's a statement down here, the alkene having the greater number of alkyl groups attached to it. That's the one that generally forms. But again, I promise I will illustrate that by example here. Okay, let me make sure I have another slide. I need to go get one. Okay, so let me just... Okay, so let me jump back over here and let's practice. Now, there's a practice problem here, dehydration of ethanol. Maybe I'll just start with that one. I'll just come back and draw that. And I'm going to draw it. You have it kind of written in a condensed structural formula way there. I'm going to just draw it since we're trying to get, familiarize ourselves with bond line and we use it so much. I'm going to draw it in bond line. And I might actually throw in some hydrogens just to kind of make this a little bit more clear. So another thing that's required in these dehydration reactions is a strong acid. Okay, and I think it's noted on the slide here. Yeah, it's usually phosphoric acid or sulfuric acid. And I want to be careful here. We've seen sulfuric acid act as a catalyst before. It is not a catalyst. It's required. And again, if we looked into the mechanism, we would see why it's required and how it's required. It provides H+ and that protonates the OH group, but don't worry about any of that. We just need to know that it is required. Often you'll see it written over the reaction arrow. It is a reactant in this case, but don't be surprised if you see it here. But we're not calling it a catalyst. It's really a reactant or a reagent. Okay. Now, what I was saying earlier, and I want to highlight this here, we don't always have to do this necessarily, especially if once you get a feel for this. I know this is kind of like not, we're going from bond line to, you know, the pseudo bond line version, but the reason I'm drawing those in is because we said that this is a dehydration, and by the way, this is a primary alcohol, right? Okay, we're going to come back to that. That's significant, right? It's the carbon attached to the OH here is attached to one other carbon, so one other alkyl group. So it's primary. Okay, more to come on that, or the significance of that. But what we said was when we're dehydrating, we are removing water, but it's really an H and an OH from adjacent carbons that we are removing. So I'm just going to circle, and it wouldn't matter. All these H's are the same on the far left-hand carbon. So I'm just going to circle that one, and I'm going to circle my OH group, and I'm going to say these really are what we're removing. They are coming together to form my byproduct, which is water, and I am replacing them with, I'll show you. I'm going to try to draw everything the way it is, but I'm replacing them now with, I should say everything else where it is, a double bond. And I don't know if it's helpful for me to actually put that in red. But basically my two hydrogens are still here, my other two hydrogens are still there. I add a double bond where I've replaced, right, I'll just write this, you know, add pi bond or double bond, and then remove H2O, HOH, right? Let's write HOH, which is of course water. So I'll write plus H2O there. So that's really what we end up with, okay? Now, excuse me. I want to look at, and these are really common examples, and in fact, they're probably the examples that are, you know, that you'll see in your textbook. But the simplest secondary alcohol, again, this is going to be important when we finish looking at these, you know, a common primary, secondary, and tertiary example. So secondary alcohol. We have seen this one recently already in our physical properties discussion. It's 2-propanol, okay? Same idea though. That carbon attached to the OH group is attached to two other alkyl groups. And I'm just going to draw in the hydrogens. Sorry, I'm drawing them smaller because I just don't have enough room. And it turns out it doesn't really matter. They are all equivalent to one another. So it doesn't matter if I circle. I'm going to do the same thing I did in the last example. I'm going to pull an H and an OH off of adjacent carbons right next to each other, right, and replace them again with a double bond. So I'll do the same thing I did. Of course, again, I need sulfuric acid to make this work, okay? What I end up with is, I'm going to try to, again, reproduce things just the way they were. I'm going to add that double bond there. I'm going to bring this methyl group, which is still a methyl group, there, and I'll add those two H's that are still on that carbon, right, this carbon over here, where they are. So this would look like this as well. Don't, you know, that's the line angle form of it, you know, there. So sorry, up here I didn't put the H's. That's not good. Okay, there they are. Okay. And this would be, you know, don't be surprised if you see it written like this, right? That's really the line angle form of what we've drawn above there. Okay. All right, secondary alcohol. Now, tertiary alcohol. Again, the simplest example of a tertiary alcohol is this one. Okay. I guess it would be what, 2-methyl 2-propanol or 2-methyl-propan 2-ol. Sometimes it's also called T-butanol. But anyway, it's tertiary, right? Tertiary alcohol, because that carbon attached to the OH group is attached to 3 other methyl groups. Again, I need sulfuric acid here. Now, I'm not going to, well, I guess we could put H's everywhere. Just show ourselves. And it turns out, believe it or not, and you could prove this to yourself by drawing this 9 different ways, but all of those hydrogens, and this isn't always the case, but it is in this example, all of those give us the same alkene. So what I mean is if I pull one H off, notice how that carbon is adjacent to this one, or that one, and the H's are all equivalent. So I'm going to pull that H and that OH off, and then what I'm left with is, I'm going to kind of, it's got to be trigonal planar, so I'm going to have to kind of redraw I mean, if I'm meant to represent it with the correct geometry, I should say, it's trigonal planar. So then, you know, these are all still there, and I guess these h's are still there. Okay, and this would look like this if we were just drawing the regular bond line structure for it. Okay, now the reason we're looking at primary versus secondary versus tertiary, and again, I'm going to go back to this slide because there's a statement here. If we're looking at this right here, what that statement or what that figure is telling us is that it's easier to dehydrate tertiary alcohols than it is secondary alcohols, than it is primary alcohols. So what do we mean by the ease of dehydration, or it's easier? Now in this case, what it really means is, and I have some empirical data to give you, is that heat is required for all of these reactions, but the harder it is to dehydrate, the more I have to heat it. And so in this case, you know, you're going to see, I'm just going to write, this one's carried out at 180 degrees Celsius, this one's like 130 degrees Celsius, and this one's more like 50 degrees Celsius, if I remember right. So the deal there, the significance of that is, this is easiest. Notice lowest heat equals easiest, easiest or easier dehydration, right? Crazier reaction conditions or more extreme reaction conditions, higher heat equals tougher, right? It's tougher to do. I have to heat it to a higher temperature in order for it to occur. So tougher dehydration. That's what we mean by the ease of dehydration. Now, there was one other thing that we really need to explore a little bit here, and if it's that last statement there. Sometimes, and I'll give you at least one good example of this, it's possible for multiple different here's that word again, or those words, constitutional isomers of a particular alkene to form. Okay, that's what we mean by isomeric alkenes here. So if that's possible, the alkene that ends up having more substituents, and we've seen that before, or more alkyl groups attached to it, is the one that is more stable. Reasons we won't go into for that, but we have a feel for now substituent or alkene substitution. And again, I'll give you a good example of this. But the one that is more stable, the one that has more alkyl groups, generally the reaction forms more of that, and sometimes just exclusively that. Okay, so shoot, I need to go get another slide to illustrate this. Give me a sec. Okay, so if we're thinking about, so here's an example. Okay, so let's say we've got something like this. Yeah, okay, that'll work. So, and we want to, we're talking about the same reaction. So the forward reaction, we need to talk about the reverse reaction, how that's possible in all these situations. But we're focused on dehydration now. So this is dehydration of, just because we'll go back and write secondary alcohol. But I want you to notice, before the examples we just used, there were multiple possible situations, right, where I could pull off an H and an OH, right? And that's true here too, but in the last examples, that didn't matter which OH and H I pulled off, it would always produce the same thing, right? Because those are symmetrical molecules, but this is different, okay? So I want to do, let's do it like this. I want you to be able to actually visualize this. So let me circle, how should we do this? Well, I'll just redraw it. I'll draw it twice. Whoops. Okay, I'll draw it out twice. So let's first do what we've been doing. So let's pretend these are all equivalent, so it wouldn't really matter which one I choose of these hydrogens on the left, I should say. Okay, so I'm just going to choose that H and that OH. Again, we're going to do exactly what we've been doing. I'm going to pull those off. I'm going to create now or draw what's left over. I'll still put that hydrogen there just because we drew it earlier. There's still 2 hydrogens here, so I'll put them here and here. And we've removed our OH group, NRH, and replaced it with a double bond, right? And again, if we want to draw the bond line, we have this, okay? All right, now, what if instead, I'm going to redraw the same molecule. Okay, what if instead I go the other way, meaning I pull off this H, and again, they are on adjacent carbons. So, in theory, I could do that too, right? So, let me go back to black here. Same thing, H2SO4. Let's write out what we have. Again, good chance to pause this and maybe practice it on your own. So, I end up with a double bond there, and then looks like, yeah, I'll keep my H's there. Okay, and we could also just redraw this as I keep saying bond line. That's correct too, but line angle. Bettelheim calls it line angle, so line angle. Okay. Now I want you to notice something. These two, well, they're the same. So these two scenarios, these are not the same. Okay, notice. Back to this statement, just to remind you of the context, right? This statement here, this bottom one, right? This is what we're talking about here. If and when isomeric alkenes or constitutional isomers that are alkenes can form, we're here, the one with the alkene that has more substituents, alkyl substituents attached, will be the one that generally forms in preference to the other. So let's think about this for a second. Here's the alkene, right? And I'm going to go, I don't know why I think it's a little more clear if you look at the line angle. Okay, so I'm going to look at the line angle in both cases. Okay, I circled the alkene itself, right? So if you'll notice, and I'll go to do a different color, up here on the top, there's only, remember, there are 4 things attached always to an alkene. They are, that has to be true, the carbons of the alkene, 4 things attached. In this case, there is only one of those. What is going on here? Only one of those is an alkyl group. So this alkene has 1 alkyl group attached. Now, what are the other things attached? Well, they're hydrogens, right? There's, and you can see it down here. There's 2 there, and then 1 here as well. Okay, now down here. Okay, let's take a look. 1, it looks like 2, 3. And they happen to all be methyl groups in this case, and the one above was an isopropyl group. But here we have 3 alkyl groups attached. Okay, 3 alkyl groups attached. And of course, the other thing attached is the hydrogen, the 4th thing. So the idea here is this, right, is the way that the reaction proceeds, and not, well, not this, or I don't want to get in the weeds here. Sometimes a little bit of this forms, so we call it a minor product, and this is the major product. Okay, but really for our purposes, we're really not so worried about the minor one usually, and we're worried more about how, the major pathway, the major reaction pathway. So let's kind of frame these reactions in that way and say, I don't know that I'll necessarily ask you for major and minor. I'm worried more about major. Okay, the major pathway and the major product that forms. Okay. All right. So, and I'm sure you'll have more examples, as well in your homework. Okay, now, this is something that I alluded to earlier, and we need to, again, expand upon this as well. It turns out that in all of these examples we've just seen of dehydration, okay, the opposite reaction is also possible. So it's a little bit misleading you know, in all of these situations where we've been using one reaction arrow, it turns out in all of these cases, we could be using double-headed reaction arrows. Okay, it's just that we were only focused on the forward reaction, which, well, in this case, we wrote it as a forward reaction, which was the dehydration. But in all of these cases, and maybe we could even make a note of that here, you know, in all cases where dehydration is of an alcohol. I just don't know if I have enough room there. It's going to get really bunched up. Or maybe it's stated on the slide. Maybe we can just just trying to decide if it's made it clear enough here. Yeah, they're competing reactions, but let's just add to that, right? Let's just say, so in all cases where dehydration of an alcohol is possible, the opposite reaction, hydration of an alkene, is also possible. Now, you would have people that take issue, certainly, with that statement. I just mean theoretically possible. Now, we're going to look at situations where one or the other direction is possible. So one other thing I'll just say here is, so double-headed arrows, equilibrium arrows, are appropriate. Now, don't be surprised if you only see a single-headed arrow, if you're looking at one or the other like we've been doing, right? We were just looking at dehydration, so we're only looking at that direction. But it is appropriate, it is appropriate to use double-headed arrows because, again, both are possible. Now, I didn't finish that last thought. I'm sorry, I'm just bouncing around a little bit, but people would definitely take issue with that statement because under certain reaction conditions, one of them is so much more favorable than the other that there's very little of either hydration or dehydration occurring. It just goes one way pretty much. But theoretically, both are always possible, and I want us to think about that as being true. That this hydration of an alkene is the opposite of a dehydration of an alcohol. Okay. Now, we do need to revisit this and Le Chatelier's principle and apply this in context. So maybe we can just remind ourselves of what it means. I don't know that it. Yeah. Okay. I don't even know the definition isn't even there. I don't know. I would ask you if we were all together if you want me to. I'll just make the assumption that you do want to revisit the definition. So Le Chatelier's principle. If a reaction is perturbed or disturbed, and this is an equilibrium reaction, is disturbed, the reaction / equilibrium, again, we're talking specifically about equilibrium events, shifts in a direction that minimizes the disturbance. So, let's go back and just, we might even need another slide here, but just for the sake of doing it, just so we don't leave anything out, and we kind of are hopefully we're tracking, we're able to apply this to the current situation, the current examples. Let's just do something generic like I've just drawn. A plus B goes to C plus D, and again the double-headed arrows indicate this is an equilibrium event. So let's say this: ways we could shift the equilibrium towards product. Now, you might be wondering, okay, well, why would I want to do that in the first place, right? And again, if we think back to this in context, when we first discussed it, probably we said to ourselves, well, if I want to make C and D, well, then I want most of the A and B to react away to produce C and D. Now, if by contrast I have C and D and I would like to make more A and B, I'd rather the reaction shift towards reactant, right? And so that's really the kind of the application piece here. This is something important that we actually do in the lab. Okay, we exploit Le Chatelier's principle to our own ends, right? If we want more product, we want it to shift towards product. Now, ways that we can do that, you may remember, are to, I'll just put add more reactant, one or the other. I'm just gonna put A or B. Now you wouldn't, if you added more of both of them, all you'd really be doing is scaling up the reaction. Now you could get more C and D that way too, but that's really not what we're talking about. So add more reactant, or you could remove product, if you'll remember. Okay. Again, if I'm removing C or D, what happens is the reaction says, well, gosh, I have a deficiency now of C and D. I've got to make some more I've got to make more of the A and B that are existing react away to produce C and D, and so that's another way to make more product, or to shift the equilibrium towards product. Now, there is a third way. I don't know that we need to. I'll just write it just in case. I'm trying to remember if we even encounter this here. I mean, these are, well, the energetics are important. I don't think we're going to talk about them really. So I'll just write it just in case. If the reaction is, I'll just put exothermic. Cool it down. Yeah. Cool down the reaction mixture. If endothermic, heat it up. Both of those will serve to shift the equilibrium towards product. Now, this is I don't think we're going to worry about this one so much. It's just that I wanted to add them so that you didn't, if you do remember this from 3A, have had this recently, you're like, well, what about that situation that I talked about? Okay, because we do typically talk about this in Chem 3A. So alternatively, ways we could shift the equilibrium towards reactant, away from product towards reactant. So in the example, in the generic example above, shift the reaction to the left, right? That bottom arrow towards A and B. So we could actually add more product. So C or D. Okay, we could also remove. I should have, remove reactant. Oops. I'll just put C or D here, A or B here. Okay. And of course, again, if the reaction RXN, sorry, that's shorthand for reaction, is exothermic, and we want to go towards reactant, we would heat it up. Okay, opposite, heat it up. If endothermic, cool it down. Okay, now, why did we do that little mini review of Le Chatelier's principle and how to shift reactions? Well, there is a no, go back to here, okay? What you see is I am able to, remember, these are competing reactions, or their opposites, hydration and dehydration are. And so notice, right, even back to here, let me come back here. And you know what I've not been consistent with? I'm glad I came back, and some of you are probably have already caught this and are asking yourselves, why didn't he finish, why didn't in all of these cases he write the byproducts? I'm sorry that I forgot to. I want to come back and do that. Let me make sure I didn't do it over here. It's there on that example. But I didn't do it there. Let me add it here. I'm sorry about that. I didn't mean for it to be confusing. I was just getting ahead of myself. And then I'm going to do it also on this one. Okay, of course, plus H2O, which we weren't worried about at that point, but same thing plus here. I'm adding the H and the OH, make the water. Okay. All right, so now if we think about these, let's just go back to here. And I'm gonna get my laser pointer. Let's just pretend we're looking back at this reaction. Okay, and we remember and we say to ourselves, well, I just learned, right, that I could replace, in theory, well, I'm just going to draw the reverse, right? I could actually replace that single-headed arrow with two arrows, right, two equilibrium arrows, because I know that the opposite reaction, right, if you're thinking about the top reaction, the forward reaction is the dehydration, removing water, right, making the alkene. The reverse, which I just added that red arrow, would be then the hydration. So let's say I wanted to favor the formation of the alcohol, right? What would I want to favor? I would want to favor the reverse reaction. So if I want to, favor alcohol, which is the reactant, right, in this case, the way I've written it, what would I do? Well, I would add more product, right? Add more product, you go to the left here towards the alcohol. And in this case, it'd be easier we may not have that alkene. Now, it is a simple alkene, and that wouldn't be hard to come by, but I could, right, add more. Easiest thing to do would be add more water, okay? Whereas if I want to favor the formation of the alkene, I could remove water, right? Now, again, in theory, I could add more of the primary alcohol as well, but the easiest thing to do would be to remove, so in this case, product, right? So favor alkene product, I could remove water, okay? And one of the ways you could remove water is by just heating up the reaction mixture and distilling it off, or doing something like that. But I could remove water, and again, I'm favoring the forward reaction, or shifting the equilibrium towards product, favoring the dehydration or the formation of the alkene in this case. Okay. All right. All right. What's next here? Okay. So another really sort of common reaction or set of reactions that alcohols undergo, okay, oxidation. Now, again, we have a little bit of groundwork to do here. We need to talk about we need to maybe revisit redox chemistry. It's going to look a little different in this context, but we do need to revisit it and maybe say a few things here. I just want to see how many slides I have. I'm sure I'll need another one here. So let's say this, okay? So in organic chemistry, in OChem, it's a little easier. I don't know if you remember back to 3A or 1A, whatever you had. Redox chemistry can be kind of challenging because we're always using these oxidation numbers, and we have to assign oxidation numbers to everything and then see whether the number went up or down, and that's what was oxidized, or that was what was reduced. It's a little easier, in my opinion, in OChem. As long as we can, again, latch on to a few fundamental principles, I think you'll see where we're going with this. So let's say this. In OChem, oxidation refers to, or let's say this will be a compound, organic compound, is oxidized or has been oxidized, when it gains oxygen and or loses hydrogen. So that's not too bad, right? Again, I think it's even easier. Now, you can use the, believe it or not, you can use the conventional method with oxidation states and all of that. But this usually works. It's a good rule of thumb, and we'll look at it, some examples here in a second. So in the same way, a compound has been reduced when it gains hydrogen and or loses oxygen. Okay. Now, and we'll a couple more things before we look at examples, because we'll look at the examples and then we'll revisit all these ideas. But let's say this. So we're going to come back to primary, secondary, and tertiary alcohols. So primary alcohols may be, this is probably, some of this may be on the slide there, converted to, okay, I'll just put carboxylic acids, again, here's a plug for knowing our functional groups, with a strong oxidizing agent, or they could be rather converted to an aldehyde with a weak or gentle oxidizing agent. I guess I made that plural to maybe A, or maybe A. One primary alcohol may be converted to A, carboxylic acid with a strong oxidizing agent, or to an aldehyde with a weak or gentle oxidizing agent. Okay, now a secondary alcohol, and we know what that is by now, right? May be converted to a ketone, only a ketone, really, with either a strong or weak oxidizing agent. Okay, and we'll look at what those are in just a second. I'm going to write them out. I'm going to look. There are lots of these. I'll give you a subset of them. And if you know those, we're good, because I won't give you any examples that don't contain those, okay? So this is nice. A tertiary alcohol isn't, I'll just put isn't easily oxidized. Now, easily oxidized. Okay, so we don't even worry about tertiary. Now, it is possible to oxidize them, but generally they decompose in the process, and it's kind of an ugly mess. So we don't even worry about tertiary alcohols. Or if you see a tertiary alcohol, and then I give you like an example where there's a tertiary, or your homework does this, an example where there's a tertiary alcohol plus an oxidizing agent, you can just put no reaction, right? Sometimes we do NR or NA, not applicable. So that would really be the answer, okay? So let's go back. First of all, okay, let's do this. Strong oxidizing, because you need to be able to recognize these. Strong oxidizing agents. Oops. Now, there are lots of these, but the common ones that we'll see, and I think probably the ones I'll give you, or I don't think you'll see Bettelheim use any other ones, and probably this is even more than he'll use. But, okay, the mixture of, this is called potassium dichromate and sulfuric acid. Okay. Sodium dichromate, very similar compound. Sulfuric acid. Let's see. Potassium permanganate's another one. I'm sure he'll have that one probably. So this is potassium permanganate, also with sulfuric acid typically. CrO3 plus sulfuric acid. This is sometimes called Jones reagent. Don't be surprised. Here's another one. Again, if you're watching these on YouTube videos, H2Cr2O4 chromic acid. So those would be strong ones, okay? And I don't think you'll see anything outside of that. Now, a weak oxidizing agent. And I would put, there are a number of these. There are less weak ones than strong ones, but oxone is, yeah, I'll just use the one, so the one that is typically used here in this context, PCC. This is called pyridinium chlorochromate. You don't necessarily have to know the acronym, just, well, I mean the actual, what the acronym means. PCC is fine if you recognize that, okay? Now, let's jump into the actual chemistry. So let's pretend we have an alcohol, okay? And I'm gonna make one up here. Okay. So first thing, what's the most important thing here, right? The first thing that's important. It's recognizing, right, whether it's primary, secondary, or tertiary. Okay. So hopefully we agree, right? The carbon attached to the oxygen is only attached to one other alkyl group, and so this would be a primary alcohol. So let's just pretend this primary alcohol is subjected to treatment with, and again, we could put plus something, or a lot of times you'll see it over the reaction arrow. So let's just pretend I use PCC here, okay? Now, a couple things that are important to recognize, and we don't always do this, but I'm gonna do it here, just because I want to again go back to this stuff here, right? This stuff here. You know, what amounts to an oxidation? What amounts to a reduction? So if I'm going to convert this alcohol into, notice, right, if I'm using a weak one, the only possibility here is that aldehydes, or excuse me, primary alcohols, if I use a weak oxidizing agent, are converted to aldehydes. And so really the only possibility here is this one. Okay. Okay, notice how sorry, that's kind of an ugly aldehyde. I'm going to try to draw it a little nicer. Not much better, but maybe a little bit. Okay, so primary alcohol, right? Notice there's the aldehyde, functional group. The oxygen stayed in the same place, but what do you notice happened? Okay, I'm missing now. Take a look, right? You know, I don't want this to be, I don't want to, but take a look. This hydrogen is now gone, and this hydrogen is now gone. Right, so remember what amounts to an oxidation, right? Notice a compound's been oxidized, just what we wrote, when it either gains oxygen and or loses hydrogen. Now it hasn't gained oxygen, but it certainly did lose hydrogen, right? And so I'm gonna maybe erase those. I just don't want them to be confusing when you're looking at this structure. But yeah, I lost. Maybe I'll just write that here. I lost H, right? Alcohol lost hydrogen, right, and was oxidized to aldehyde. That's a good summary statement there. Okay, now what if we'd have taken that same alcohol, so I'll just redraw it here, we might need more room here, and I had instead used one of the strong ones, and I'm just going to choose one. Any of these would work to do this. So I'll just choose Na2Cr2O7, the sodium dichromate with the sulfuric acid. Okay. And again, fortunately or unfortunately, I mean, it's a little bit of a bummer. You have to, this is good flashcard material. You have to be able to recognize these oxidizing agents, or, you know, if you're asked, okay, how would I make this compound? You need to, be able to write out, well, here's an alcohol, and here's a strong oxidizing agent that I would use to do it. Okay, so but instead, right, if you go back to our definition, I won't keep referring to it. Instead of now an aldehyde, we end up with a carboxylic acid. Okay, and you know what? Let me just write it sideways there. Sorry, OH right there. Okay, I end up with a carboxylic acid. So. But in the same way, right, I lost. So not only did I lose two hydrogens, and I lost the same two hydrogens. If you think about what we have over here, right? I again lost those same 2 hydrogens as before, but I actually gained an oxygen. So here, the alcohol lost hydrogen, 2 of them, right? And gained oxygen. So this again fits our description of in this case oxidation. So again, was oxidized, in this case not to an aldehyde, but to a carboxylic acid. Okay. All right. So good example of a primary alcohol, both being oxidized in a couple of different ways, with a weak oxidizing agent and with a strong one. Okay. Maybe I have enough room to do, a third example. And of course, a third example would be that other category that we just looked at, right? Not tertiary alcohols. They don't do anything, right? But interesting at least, but secondary alcohols. So they are converted to ketones. So let's do a secondary alcohol. Well, let's do it like this. I'm just going to make it kind of obscure. All right, the reason I did that is, again, I want you to recognize that as secondary. You're tempted to say it's tertiary, but it's actually a secondary alcohol. So I'll put secondary there. Should have put primary over here. Well, it's the same one as before. So, but again, let's say we use in this case potassium permanganate and sulfuric acid. Again, weak PCC would work here. Any of the other strong ones would work here. We're just choosing that one. Okay, and again, if you'll notice, I'll just do this just to do it. There is an H there. So if I'm converting, oxygen stays in the same place. I'm looking for the corresponding ketone in this case. So everything else is the same except for, again, I have removed just those 2 hydrogens and replaced them in this case with a double bond, as before. But yeah, this is a ketone. So we can again say something like alcohol lost hydrogen and was oxidized to a ketone. I'll write it out. Okay. Now you may be wondering, and rightly so, you may be wondering, well, what happened to that hydrogen, right? Or over here, right? Or over here, or over here. Again, we would have to look at mechanisms, and we could. These are really complex mechanisms, believe it or not, and look at what's actually happening to the pyridinium chlorochromate and the chromium and the manganese. They actually, yeah, it's a really convoluted thing. We would muddy the waters if we looked at that, and I don't care that you know that in this case. It's really of little consequence. What's important is recognizing what got oxidized, and meaning the different types of alcohols, how they got oxidized, and what they got oxidized to. That's really what I care about in this case. Okay. And again, if you maybe saw, just to be clear, I said this earlier, but let's pretend. Sorry, I don't mean to. Let's pretend you did see a tertiary alcohol, right? And I gave you, some sort of, I gave you one of these, right? So we're back to like K2Cr2O7/H2SO4, or your homework did this on exam, and the idea here is you'd need to recognize, oh yeah, that is tertiary, right? And you could write no reaction, or, nothing interesting forms, or, Na, not applicable here, okay? So that would be the idea there. Okay, so next thing, ethers. So, another class of oxygen-containing compounds, but, in contrast to alcohols, they're, if we're thinking back to our, how we represent this sort of generically, it's ROR, or, put the lone pairs there, or, an oxygen sandwich between 2 alkyl groups. And you see some geometry stuff here. Of course, this is a bent molecular geometry, and so because of the lone pairs, it's a little bit different than ideal. But yeah, you see that the electron geometry would be tetrahedral, but the molecular geometry would be bent. approximate bond angles of 109.5, but slightly different, right? Because of those lone pairs. Okay, little bit of nomenclature here, right? Because again, new functional group, we're always adding little, additional stuff so that we can name these different, newly encountered functional groups. There are two ways to name ethers. One of them is a lot more convoluted, and I don't even remember if Bettelheim addresses it or not. But we're gonna deal with common names, and this is way easier. And you'll see why. All we have to do is figure out, if I get my laser pointer here, figure out the names of the R's, the alkyl groups attached to oxygen, alphabetize them, and throw the word ether on the end. So really a lot simpler than a lot of other functional groups that we've encountered thus far. Good, I have a slide there as well. So if we're thinking about this one, maybe we'll do ethyl phenyl ether on the next one. So really, again, all I have to do is look at the two R groups attached, and I think you'll agree they're isopropyl, right? These are getting more and more familiar to us. And then ethyl. And here's another good reminder, though. Remember, isopropyl has an asterisk next to it in the sense that the I in iso is used to alphabetize isopropyl or any iso whatever group, but all those other prefixes, like the Greek prefixes in like in tert-butyl or sec and sec-butyl, all of those are not used, but isopropyl is. And again, we didn't make that up. We were, that was that was made up by the powers that be. So, but anyway, ethyl comes before isopropyl in any case, or it comes before iso or propyl, so it wouldn't really matter. It's just a reminder. This becomes ethyl, isopropyl, ether. Okay. Ethyl isopropyl ether. Make sure I got that. Yeah. Let's do this one on the next slide. Ethyl phenyl ether. Okay, and for this one, it's named back to structure. So again, pause it, give it a try. I'm just gonna go for it here. So there's my ethyl, and again, a phenyl group, remember, is essentially a benzene ring attached, or being named as a substituent. So this would be ethyl phenyl ether. Okay, let's try one or two more, just for the heck of it here, since we have a little room. Let's do something like that. Okay. Good chance to pause, give it a try. So my alkyl groups are these, right? This one and this one. And to me, I'm looking at this one, I'm saying that looks like secondary butyl. And this looks like propyl, not isopropyl, just regular old propyl. So putting it all together, remember the sec doesn't count in this case. Iso would, but sec doesn't. So this is sec-butyl, because we actually think about butyl when we alphabetize. Propyl ether. Okay. Yeah, and I mean there's a lot. Let's just stop there. There's a bunch of different possibilities, and you'll encounter more in your homework. So let me make sure I get sec-butyl propyl ether. That looks good. Okay. Now, not a ton of other stuff that I want you to know about ethers. Really, some of the other stuff that I want you to know is really just here on this slide. One of the things, in organic chemistry, we're always interested in how things translate to the lab, or what kinds of compounds are interesting or helpful to us in the lab. Ethers are really good organic solvents. They have kind of intermediate polarity. They actually lean towards non-polar. And so if you go back here, and this is an interesting point of discussion here, if we get our laser pointer, if you look at this molecule, and I think I've even mentioned this, seems like I mentioned this at one point not too long ago, there is a dipole moment, okay? Because if you're thinking about, this dipole and this dipole, okay, they add together to a net dipole moment. So there is, the ether functional group is technically a polar functional group, but, okay, there's lots of, but ethers possess nonpolar groups on either side of oxygen. Okay. Okay. So, and the larger those nonpolar groups are, and I can write that. The larger they are, the more ethers behave like hydrocarbons. Okay, like even small, and I have a little room here so I can do this. Even small, this is called diethyl ether. Relatively small ethers like diethyl ether. If you think about putting some diethyl ether in with some water, it actually forms two layers. So it's not at all miscible with water. So if you think about the solubility of ethers, they're not usually terribly water soluble. They also, because we just said they act in some cases like hydrocarbons, they have relatively low melting points and boiling points, and those things are listed on this slide as well. And then just some other stuff that's interesting about them is, they're real flammable because it turns out oxygenated hydrocarbons, meaning a compound just with carbon and hydrogen, but then that also has one or more oxygens. These are usually really flammable. If you think about our gasoline, I don't know if I mentioned this before, but if you go to your pumping station, your gas station, you've probably seen there's sometimes little placards or little stickers that says contains up to whatever percent, 10% ethanol, or even higher in some cases. And the reason that ethanol has been used as an additive, one of the reasons is you actually get more efficient burning. So the oxygenated fuels are more flammable, they burn more readily, and they actually provide more complete combustion of that fuel, and you get less pollutants, less byproducts. So less crap coming out of your tailpipe and all that. So, but anyway, oxygenated hydrocarbons are really flammable, and ethers are among those. And then there's some other stuff about how they're not terribly reactive, which makes them really good solvents as well, organic solvents. So, okay, now here's what I want to do, and I've been doing it. I've done it both ways, but in recent semesters, I've actually been not covering thiols in this chapter. So alcohols, ethers, thiols, but then I've just like I said, in recent semesters, cut out the thiol stuff, partly just because of the volume of information, partly also because one of the main reasons is we encounter thiols later in our organic or biochemistry. Excuse me, not the organic, in the biochemistry portion of the course. It turns out they're important functional groups when we talk about amino acids and proteins, and so later on, we get this thiol stuff, most of the same stuff anyway, maybe not some of the ancillary stuff, but enough of it so to where we are able to latch onto what a thiol is. So let's just do this. Let's just say for chapter 5 we're only going to be concerned with alcohols and ethers, and let's just not worry about the thiol stuff for now. Okay, so let's you get a little bit of a reprieve here. Let's stop the chapter right here. Okay.